In this lesson, we will continue our discussion of derivative rules by talking about exponential and logarithmic functions. Let's first off take a look at the exponential function a to the x, with a being bigger than 1, and try to come up with an idea of what would the derivative look like. So here's a few properties you might bring up. First off, you'll notice that the function is increasing and concave up. Remember, when a function is increasing, that means its derivative is a positive function, meaning it would lie above the axis. Also, since the function is concave up, that would normally mean that the second derivative was positive, but we also knew that that meant that the first derivative was actually an increasing function. Let's also talk about the slopes. Notice that the slopes are rising without bound on the right. Further, on the left, there's some sort of asymptotic behavior. Not only is the function going to 0, the slopes are going to 0 on the left. Now let's imagine what a function would look like that was positive, increasing, rising without bound on the right, and going to 0 on the left. Well, that's actually a description of the graph. The graph that I see here, it not only looks like itself, but it also would have its derivative looking like itself. Interesting. The long and short is that the exponential function derivatives tend to have similar shapes to their original functions. Let's dig deeper on that. Here's a picture of the graph of 2 to the x, and we can estimate f prime of 0 using our standard trick to say that f prime of 0 is about 0.693. And then notice that f prime of 0 would actually be the same as that number times f of 0. So we're taking a guess that turns out to be right, that the derivative will actually just be this multiple from f prime of 0 times the function itself. Based on that, this would be the derivative of 2 to the x, which is basically the same shape, just a little bit lower. For 3 to the x, f prime of 0 on 3 to the x would be this number, and that number is just scarcely above, so that this is almost exactly the same curve. But now it's above. So the thought process is, there's also a place where you would have a number where it's exactly the same, and that number would have to be between 2 and 3, probably closer to 3. That number actually turns out to be e. So it turns out that this e, which is approximately 2.718, has this property. And again, this is something that's proven by that definition from the previous section, that the derivative of e to the x turns out to be e to the x. Similarly, another rule that comes out of this is the derivative of a to the x for any positive base would just be the natural log of a times a to the x. The derivative is a multiple of its own function, and that multiple is the natural log of the base. So this gives us two new derivative rules. Another one that's helpful, which is proven at the top, is that it turns out that if you have e to the kx, the derivative of that would just be k e to the kx. The reason for that is that if you have a power to a power, you could multiply the powers. So doing it in reverse, e to the k is just a number. That means its derivative would be the natural log of this base, e to the k, times e to the k to the x, the rule that we had in the last slide. But the natural log of e to the k is just k, and then the e to the k to the x, we can then multiply them back, and that's a little proof of this. Let's do a couple of quick examples. F prime of x. For this one, the 5 is a coefficient, so I'm just going to leave it in front and focus on the rule for 3 to the x. The rule on the previous slide said that anything to the x power, a to the x, was the natural log of a, so in this case we have the natural log of the base 3, times a to the x, which was again 3 to the x. We also know that the derivative of e to the x is just e to the x. So we get a quick answer from following those rules. The next one, when we take the derivative of 5, that's 0, so it goes away. When we take the derivative of 2x cubed, the 3 is going to come to the front and give us a 6, and then we have an x, subtract 1 from the power to get squared. Then we have minus 7. It's a coefficient. And then this one is the e to the kx. So the k is the negative 0.3. When I take the derivative, I get k e to the kx. And just simplifying that a little bit, let's write this as 6x squared plus 2.1 times e to the negative 0.3x, just multiplying together those coefficients. Now let's talk about the logarithmic function. I'm going to write a few things about the function involving increasing, decreasing, concave up, concave down, and slopes. So here's a few characteristics I grabbed. First off, this is an increasing function. Secondly, it's a concave down function. Then as we look at the slopes are getting more and more shallow as we go to the right. And as we go to the left, which is basically approaching 0 from the right, these get extremely large, almost vertical. So they're rising without bound as we approach 0 from the right. If I was to try to draw this graph, then because the function is increasing, well, f prime of x, that would make it a positive function. It would be above the x-axis. Since it's concave down, using what we said earlier, that would mean that it was a decreasing function. So it's positive and it's decreasing. It's getting shallower on the right, so the slopes, which in this case would be the derivative's y values, would be going towards 0, but in some sort of decreasing fashion. And as we go to 0, we would see them rise without bound. Here's a picture of roughly what that looks like if we describe it. And that graph turns out to be the natural log of x goes to 1 over x when you take its derivative. So 1 over x is the derivative of natural log of x. We do insist that x is bigger than 0 because the natural log function isn't defined there. With that, let's take a few more derivatives and practice a little bit more. Y prime here would be 7, and then the natural log of t, remember 7 we can leave in front. The natural log of t would be 1 over t, because again we just had the natural log of x, would become 1 over x. We said the derivative of e to the t is e to the t. For the 4t squared, I'll bring the 2 to the front and get 8. Then we have t. And the 1012 is just a number, so it's going to disappear and become 0. A final answer I might write to clean this up slightly would be 7 over t plus 5 e to the t minus 8t. For the next one, we're back to a point where actually some of these are a little bit strange. Namely this one, this 1 over x squared and the square root of x cubed. When I ran across these earlier, I had to rewrite them in order to take their derivative. Let's do that first. 3e to the 2x minus, this is going to be x to the negative 2 when I rewrite it. 3 natural log of x. And then remember for these, you might recognize the square root is going to be like a 1/2, but the cube power is part of that too. Remember, top is the power, bottom's the root. This is actually 3/2. 3 for the power, 2 for the root. Now we can take the derivative here. So f prime of x will equal, and then let's just follow through with all of our rules. The 3 I'll leave in front. We have an e to the kx here, which would be k e to the kx, and k equals 2. Then for this one, I'll bring the negative 2 to the front and subtract 1 from the power. Negative 2 minus 1, again, be careful with negative numbers, but negative 2 minus 1 is negative 3. The natural log of x, again, the derivative is 1 over x. And then the x to the 3/2, I'll bring the 3/2 to the front. And when I subtract 1 from 3/2, I get 1/2. So just to do some cleaning, I'm going to say 6e to the 2x. This is going to become a plus 2 over x cubed. I'll bring that back down. We'll say plus 3 over x. And then for the last one, I'll say plus 3/2 square root of x. And that'll be my final answer for this derivative. Now let's look at a few applied problems. The population of Nevada can be approximated by 2.020 times 1.036 to the t, where t is since the start of 2000. We want to know at what rate is the population growing at the beginning of 2009, which, by the way, that would be t equals 9. Now the word rate is referring to the derivative, so we need to put the derivative together here. P prime, well, the constant is still there, the 2.020. Now this is the a to the t one. This is always the natural log of the base, which would be the natural log of 1.036, that's the natural log of a, times a to the t. And then we'll just plug 9 into this. I arrive at a value of 0.098218, and let's figure out what these units are. P was in millions, and the derivative is always a quotient, so I also need to divide by years, which was the variable's units. Now, I don't really like this one, so let's rewrite this in something that makes more sense. Let's say 98,218 people per year. That looks a little bit better than this small decimal of millions. Now let's do a tangent line problem with one of these. Let's find the tangent line to the graph of natural log of x at x equals 2. Remember, there's 3 steps. Step 1, find the slope. For the slope, I will do f prime of x first, and remember the derivative of natural log of x is 1 over x. Then for the slope, I'll simply take the 2 value that I'm given and plug it into the derivative to say the slope is 1/2. Step 2, find the point. So I'm going to do f of 2, which is the natural log of 2, and that is approximately 0.693. That gives me a point of 2, 0.693. So given the point and given the slope, we'll now find the equation of the line for step 3. Y minus your y coordinate, 0.693, is equal to the slope times x minus your x coordinate. Let's distribute the 1/2 to have y minus 0.693 is equal to 1/2 x minus 1, and then add the 0.693 to both sides to get 1/2 x minus 0.307. That's the equation of the tangent line. And let's draw it also. We've got the point at 2 that we were given, and we even can just kind of grab that y coordinate. But then the y-intercept was somewhere around here, this negative 0.3, and then we can draw the equation of the line. So there's a pretty good tangent line for this function. For our last example, let's do an interest problem. Suppose we have $1,000 deposited into a bank account that pays 4% interest. And this is compounded annually. That's important. So P0 is my 1,000. My R would be 0.04 because, again, you want to change that to a decimal. And let's find a few values here. First off, because it's annual, the formula is P is equal to P0 times 1 plus R to the T. The way this one wants us to do this is call it f of t and plug in our values. So we have f of t would be our starting point, $1,000 times 1 plus 0.04, and we don't have a value for t. Here's a little bit of a simplification on that. Now we're asked to find and interpret f of 10 and f prime of 10. F of 10, we would just simply plug it into the function. If I do that, I get $1,480.24, which simply means that the balance after 10 years would be $1,480.24. Now we're also asked to find f prime of 10. Let's first find f prime of t. The coefficient will stay in front, this 1,000, and then we have the natural log of your a, 1.04, times a to the t. That's your usual rule for the exponential function. Then we'll plug 10 into this, and we have the following. This gives me $58.06, and that's actually in dollars per year. So the interpretation of this would be the same as we usually do for derivatives. It's the concept of next, or in other words, the 11th year. The 11th year will bring an additional $58.06.